I will just briefly introduce this webinar before handing over to my colleagues to present the work that we've been doing. Some points before we start. So this meeting is recorded, and all the content, slides, and recordings will be made available afterwards. We do want to be interactive with you, so please raise any questions or comments that you have in the chat, and we will have a couple of time slots during the webinar to try to answer as many questions as we can. Maybe 2 sentences on the 5G Smart project if you're not aware. So it's a European Horizon 2020 project where we look into 5G for smart manufacturing. And we have 3 different trials across Europe. And in one of the trials in Kista, Stockholm, we focus very much on robotics. And then that's the work that we will now try to describe to you in this webinar. The outline of the webinar. So I will shortly hand over to Ognjen and Pietro and Karam, and they will present the use cases that we've been working on. And then Peter de Bruin will present the Kista trial site and the radio deployment there. And then finally, we will have a panel discussing future robotics and cellular communication. And then at the end of the webinar, we will have then a Q&A as well. So with that, I hand over to Ognjen and Pietro.
Yes. Thanks,
Okay.
Krister. Then I share the screen. Okay. Yes.
Very good. So I will start. Good afternoon, everyone, from my side as well. Welcome to this 5G Smart webinar. So my name is Ognjen, or short Ogi. I'm with ABB Corporate Research in Sweden, and I'm leading work in 5G Smart around development of advanced use cases on industrial robotics over 5G. I will start this part of the webinar by putting this work into the context, and then I will first hand over to my colleague Pietro, who will present work progress and major achievements done so far around the development of the mentioned use cases. And then also at the end of this slot, we have our colleague Karam, who will present our development work around a use case on augmented reality-based visualization on the factory floor. So, Pietro, if you can go on the next slide, please. I would just, before we start, just would like to point out that after this slot, so basically after showing you main results from our practical work, we'll also have a Q&A slot where you are feel free to enter your questions in the chat, and then we'll have speakers addressing your questions and providing comments. So to put this work into context, when we look at industrial robotics as a business domain, it has also been undergoing a transformation, which has been mostly driven by the Industry 4.0 movement, and then also the different requirements on, for instance, digitalization. And then when you look at some of the major technological trends there, we see the need for different enablers in industrial robotics. So, for instance, when we look on ease of programming, there is a need for a non-technical person, non-experts, for instance, to be able to program a stationary robot to do a certain task, for instance, on a factory floor. Or when we look at collaborative applications, there we see a move going from collaboration of robots more and more going towards collaboration of robots who are working side next with human workers, for instance, on the factory floor. All this basically we have addressed to some extent during development of our use cases. Next slide, Pietro, please. So in this part of 5G Smart Work, we have been working on developing 3 distinct use cases over 5G. And all 3 of them they combine a collaboration of stationary and mobile robots. They also introduce or address different aspects of interactions between robots and human workers on the factory floor. They also include a machine vision support system and also augmented reality-based visualization of factory floor information. And all these use cases, their implementations will be trialed for 5G in our reference site at Ericsson's Smart Factory in Kista. Next slide, please. So, please go back. Yeah, this one. Thanks. When we look at business and research motivation, there we would like to explore capabilities of 5G, both in terms of technical features, but also architectural capabilities, to see how they can support advanced use cases on industrial robotics. And there we are motivated by the promises of 5G being allowed to offer industrial grade wireless-based communication infrastructure, coupled together with providing a native support for edge computing. With these plans, with these promises, with these ambitions, we actually expect from 5G to allow full-scale mobility, which is especially important for our mobile robots. Then also increasing structuring flexibility, not just in terms of removing the cables, but also allowing production lines to be reconfigured in an easy way, and all the way to, for instance, decreasing total robot footprint, but by offloading a part of robot control functionality from dedicated robot hardware into more close or distant edge or cloud platforms. Next slide, please. So this slide will show you a reference technical setup for this part of 5G Smart Work. This setup is driven by the vision of 5G powered industrial robotics, and it assumes that main end devices are connected over 5G to the rest of the infrastructure. So we have 2 stationary robots. We have 1 mobile robot or 1 AGV, 1 smartphone, and 1 AR-based headset, which are all connected over 5G. Next slide, please. At the core of this vision, we look at offloading a part of robot control functionality from dedicated robot hardware into close edge platforms. So here we offload certain key robot functionality, such as navigation for mobile robots into the edge cloud, but also, for instance, motion planning for stationary robots or stationary robot arms. We also, for instance, offload a central task planner or task manager, which kind of coordinates different tasks between different types of robots. Next slide, please. Also, one other distinctive feature of this setup is a machine vision system, which relies on video cameras, which are off-board or external to any of the robots, which kind of overlook the whole testing area, and then which support in providing different machine vision features, such as object detection and object localization. Next slide, please. I would just briefly reflect also on the main equipment that we have been using in this work. So we are doing most of the use case development for the first 2 use cases. We do it at ABB Corporate Research Center in Sweden. Here locally, we have an in-house mobile platform, mobile AGV. Next slide, please. Which runs, so it has an onboard computer, which then runs some low-level robot control functions, such as, for instance, inverse kinematics, servo control, etc. Next slide, please. Then we have onboard safety module, which is there, of course, to facilitate safety towards human workers working around this mobile platform. Next slide, please. Then we have front and back. We have 2D lidar sensors, which then allow the mobile platform to have a perception of the environment. Next slide, please. Then we have a transportation plate, which is used to transport an object in one of the use cases. And then lastly, we have integrated this mobile platform towards 5G by employing a 5G industrial router. Next to this one, we have ABB's single arm Yumi, which represents a stationary robot. Here on the next slide, please, on the left side, you can see Yumi controller box, which is running low-level motion execution for this stationary arm. Next slide. Then we have two types of cameras which support some machine vision features. Next slide. Then we have a testing object which is being transported by the mobile platform. And then lastly, we have also integrated stationary arm towards 5G infrastructure. Then we have a separate workstation which runs robot control software and acts as an edge server. And then lastly, we have next slide, please. We have a private on-prem 5G system which we have acquired from Ericsson and that we use for development and functional testing purposes. And this private system also employs several radio access points or radio dots just to extend the coverage of 5G system. Some more details on the 5G system itself will be provided by our colleague Pietro from Ericsson. And with that, I will hand over now to Pietro to walk us through development of the first two use cases. Pietro, please.
Yes. Okay. Thanks, Sobi. So yes, I will describe. This is one of the use cases called the machine vision assisted real-time human-robot interaction over 5G. So here, what are the elements of these use cases? First of all, there is the lead-through teaching of robot grasping. So why we are interested in doing lead-through teaching? Because especially in a small company or in startup, or even if we want to use in the future the robot in other application, we need a way to program the robot in an easy way. So one of these use cases we are considering is to use a tool for everyday life that everyone can use, and this is of course a smartphone. So what we do with the use case, we for the robot to grasp an object, we lead using the smartphone. We show and teleoperate the robot with the smartphone how to pick up this particular object, and then like this, so the robot can pick up the object, and this let's say this use case, when the position of the object changes, so the robot can adapt to the new position of the object. So what are the elements of this demo? First of all, there is a marker on the robot and effector, and then we have a smartphone. So let's say the smartphone will recognize the position of the marker, and this way, let's say, estimating the position of the marker, moving the smartphone, we can, let's say, program the robot such that the robot will follow the movement of the smartphone. And then we need we have also this video camera that has object detection and localization modules. So what happens that with this module, we recognize the object in the scene. So for this system, not only is important the position of the robot, but also the position of the object. So the object should be detected, and then for each object, the robot learns a skill. And for each object, we can associate a strategy of grasping of the object and also a skill, so what the robot should do with this particular object. And of course, everything, as also mentioned, run on the edge. All the planning part of the robot will run on the edge. And also, the smartphone is connected via 5G. So if we go in the next slide here, we can show in brief how this demo works. So in practice, now the user is showing by teleoperating with the smartphone how the robot can pick up this cube. So with the application on the smartphone, the user can show, let's say, different via points of the robot, different strategy to pick up the object, and particular motion strategy to place the object on the mobile robot. Yeah, so this with this procedure, the teaching is now completed. So the robot now learned the grasping, and later on we show how the robot execute what it learned. Now let's go a bit more in detail about how it technically work this demo. So we have a camera here that estimate the pose, which means position and orientation of the robot. And then this is the marker that is on the robot that is used for the lead through. So what happened here? The principal point, the principal challenge is that the robot learn a trajectory in a reference frame that is fixed on the object. So once he learned this reference frame and this set of via point in the reference frame fixed on the object, if we move the object in the workspace, so if the position of the object changes, then the same skill can be reused also for different pose of the object. While in industrial classical lead through, this when we do this lead through classically, it is applicable only for a single pose of the object. So here we tend to be more flexible with this system. And then we can associate to each object a grasping strategy and also a trajectory to tell the robot what to do with this particular object. So this is, and then of course, this is an environment that is not fully structured. So it's called unstructured environment partially, so that the robot does not know the position of all the elements in advance, but it has to use sensors to estimate the location of all the relevant objects. And these are let's say, a challenge in the system. And this very quickly is how the app look like. So there are different, let's say, button and command that the user can do to open the gripper, close the gripper, define via point through which the robot should go, pick object, drop, and also this app supports also mobile manipulators and multiple manipulators. So if we want to lead through different components of the robotic system, we can switch easily from one component to another. For example, from first arm to second arm, or even the base. So this adds some flexibility. And then we can go to this other use case that is called the remotely supported collaboration of 5G connected robot. So here we have this mobile robot navigation, vision assisted docking element. So here we have the robot that navigate into the environment and also avoiding obstacles that the robot does not know in advance. And then the robot has a module that allow to dock in a more accurate way in the workstation. So, and here we can see, as also Guy was mentioning, we have many of the module for navigation on the edge. For example, we have this module called simultaneous localization and mapping. With this module, the robot can create a map of the environment and localize itself within the map. So called also SLAM, which means a module that the robot used to create the map of the environment. Then we have the mobile robot navigation, which is all the module that plan the path of the robot also by avoiding obstacles. And there is localization that allow the robot to localize itself within the map. So once the map is already created, the mobile robot localization module allows the robot to estimate its own position within the map. And also general task planning means the robot has a sequence of action to perform to fulfill its general task. And so this module will take care of planning what is the right sequence of tasks to perform. And then also the stationary robot motion planning, which will control the movement of the mobile of the YUMI, single arm YUMI. And then also here, what is the benefit of 5G? That we can have a fast and reliable communication, both for grasping execution and for mobile navigation and docking. So for robotics, this is very important because without reliable wireless communication, the movement of the robot will not be smooth, or the robot will stop due to, let's say, the safety mechanism within the robot. So it's very important here, this usage of 5G, especially for the mobile robot, because we cannot have wires in any case. So this is very important aspect. And then there is also vision. Since the environment, as we said, is not fully structured, it's important to use cameras to localize, to estimate the position of the relevant objects in the scene. But here, let's see more in detail how the demo looks like. So here we see that the robot is navigating, a human come into the environment, and the robot does not stop. So classical robot will stop, but this in this system, we try to avoid obstacles that are unexpected. And now the docking procedure will start. So the robot dock close to the workstation, and then the grasping procedure will start. This is the execution. We did the teaching in the video before, and now we are executing what we teach to the robot. Yeah, now the robot received the component, and then it goes back. This is called undocking, so it's the opposite of the docking. And then we can see as the robot can go back in its initial position. Yes. So if we go ahead, so some detail more about this part of mobile navigation. So how it works, the system. First of all, the robot creates a map of the surrounding environment using this module I presented before called SLAM, Simultaneous Localization and Mapping. And here in the picture, you can see the map that the robot creates. So how the robot perceives the environment around it. And then once we have the map, we have to plan the motion. So we want to go, if we want to go from A to B within the map, we need to plan the motion. And for that, there are two modules, the global planner and the local planner, that in this demo are both on the edge cloud. So the global planner will take care of defining a path from A to B. So no velocity, solely a path that will avoid the obstacles from a point A to a point B. And then there is the local motion planning that takes care of computing the velocities such that the robot can follow this path that was assigned by the global planner. And also the local motion planner takes care of avoiding also obstacles that were not in the map. So if a new obstacles appear suddenly or was not considered in the map, the motion of the robot will locally change in order to avoid this obstacle. And this system is based on ROS navigation stack, what is called the ROS navigation stack with some modification. We did in-house, but the basics are in this ROS navigation stack. ROS is a robot operating system, and is a middleware for robotics that facilitate the integration between many components in a robotic system. And then what happened after the global and the local planner compute the velocities that the robot should, after the local planner compute the velocities that the robot should follow, from the edge, these velocities are sent to the mobile robot. that execute these velocities and then actuate the motion through the local servo control. And on the other end, the robot send LiDAR signals to the edge cloud, because if some obstacle is to be avoided or the robot needs to localize itself, so the global planner, local planner, and the localization modules, they need this LiDAR information so that the robot can operate in the environment. And but what is a feature of this system, that the localization or error is in the order of few centimeters. So if we command the robot to go in a given workstation, the position of the robot will not be completely accurate or accurate enough for the picking task. So we need another module, that is the docking module, that as the docking module, let's say, position the robot in a more accurate way close to the workstation. So, and here I say a bit more about the docking. So how the docking happens. Here there is the docking marker on the robot, and this is the docking camera. So as I was saying, what happened, that the robot navigates in proximity of the workstation, of the stationary robot, and then the control of the robot goes from the planner to the docking module. To docking module, and the docking module takes the control of the robot. So such that the position of the marker on the robot desired is equal to the actual position of the marker. So it's a kind of a closed loop control algorithm. So this docking module exactly take the control of the robot. So this is very important, such that the robot can be placed more accurately close to the workstation. And this position of the marker, this position and orientation of the marker on the robot here are estimating using RGBD images from this camera. So this camera is an RGBD camera, but we use only the RGB part to estimate the pose of the marker. And then using this information, let's say it's like the workstation through the edge cloud take the control of the robot, as I mentioned, drive the robot close to a position when the object can be placed or picked on the mobile robot. So this also is a case of, let's say, unstructured environment. And then here something about the robot grasping execution, which is the last module we can consider. So this is the camera for the teaching and execution. We use two cameras because with only one camera it's difficult to, let's say, have a good view of both the, let's say, the docking field of view and the grasping field of view. So we use two cameras to have a wider field of view for our system. And then what happens that in the teaching phase, the robot learned some specific via point and a grasping strategy for the object, using to pick up the object. And then once the robot has this skill, find the object using the RGBD camera. So in this, exactly, find the object using the RGBD camera, and then also facilitating by the marker on the object, and then compute, express all this waypoint in a reference frame that is fixed on the object. And then it can create the trajectory. So this trajectory, this motion planner is executed on the edge cloud and send command to the robot controller. So via external guided motion, EGM. So EGM, which is interfaced with the ROS, with the ROS system. And like that, the robot can execute the grasping in a robust way to variation of the object pose, of the position and orientation of the object. Yes, this was the last slide.
Thank you very much, Ognjen and Pietro. Then we have some time for questions. So again, if you want to post a question on the chat, please go ahead. I don't think I don't see any questions at the moment. So maybe I can then start with the question. Regarding the lead through programming, and you also mentioned this, that I mean, from a non-robotics person like myself, it looks fairly easy and smooth to do it. Could you say something on the sort of limits with this approach? Are there limits in terms of accuracy or things that you simply cannot do, that you need to use some more traditional way of programming the robot?
Yeah, definitely. If we want very high accuracy in the system, yeah, this is limited. For example, with classical industrial tasks, or with, for example, assembly or pegging all tasks, or tasks that require very high accuracy of millimeters, then this is not the best way. But for tasks that, let's say, in industry or also in service application, which there is no very high accuracy required, then this can be a good way. Also to avoid that the customer has to call a robot programmer to come up with the program for the robot. So for simple tasks, this is a very, I think, can be a good solution. And also when the system is more complex, also is very good. Imagine, for example, a mobile manipulator with base and 2 arms. So with this approach, you could switch from base to arm 1 to arm 2 in a very quick way. So yes, these are the, yes.
Yeah. And I see that we have a couple of questions on the chat. One question is regarding the LiDAR that you mentioned that we use. So how often is the LiDAR information transmitted to the cloud?
You mean? Yes, this. So let's say that the local planner work at 20 Hz. So with the LiDAR, we need at least to be at this frequency, so the local planner can avoid unexpected obstacles. So
right.
let's say at least 20 Hz should be.
Yeah. Okay. And then there is a question on this robot learning, if that is AI-based reinforcement learning.
Okay, this you mean the learning? This is not reinforcement learning based. This more programming by demonstration based. Reinforcement learning, we could use reinforcement learning later on to refine the result.
Yeah.
Yeah, but this is based on programming by demonstration. Then if we see that the robot fails, the robot could, by self-learning, by trial and error, try to refine the execution phase. But for now, we have only the programming by demonstration step.
Right. We also got a question, I guess it's a more general question on the requirements on the 5G communication in terms of latency, reliability. Do you see that these are high requirements or?
So for the robot system?
Yes, I guess so. It didn't specify which part of.
Let's say in this particular setup, let's say in terms, for example, let's pick the mobile robots. Since we have this local planner that send commands at 20 Hz, so the communication system should allow at least to, let's say, send this command in a reliable way at this frequency. So this is one important requirement. So yes, actually, and the more stable is the frequency, the more smooth will be the motion of the robot. Yeah. Then if the robot does not receive, for example, 2, 3, 4, or 5, this can be set in the robot controller command. Then it stops. For example, this is a typical safety measure that we can make the robot stop is if a number of consecutive packets are lost. So yeah, but let's say the basic requirement is for the robot is for example 20 Hz velocity command. This should be guaranteed. Yeah, and also for the manipulator we have similar. For example, if we want to run at 4 milliseconds, is a typical frequency of EGM, then we should make sure that 5G deliver this velocity command to the arm as more stable as possible.
Right. So I see, Ognjen, you turned on your video.
Yeah, I just want to maybe to compliment Pietro a bit regarding reliability, or I mean, when you look at general communication service availability. So we haven't been specifically talking about the number of nines, but we see a clear requirement on reliability, meaning that when we look at this communication from the edge towards either stationary robot arms or mobile AGV, then basically you could only allow 2, 3, 4 consecutive packets either being lost or breaching required the latency threshold, which we see as a quite demanding requirement onto a communication system part.
Okay, very good. Good. Thanks, guys. I think we should now move to the AR use case and Karam's part of the presentation.
Yes. Hello. Let me just share my screen. Just a minute. Hopefully you can see my screen.
Yes.
Great. So hello, everybody. My name is Karan Takedini. Welcome to this presentation of the new application AR visualization and control for ABB robot. So let's explain it a bit. So the main purpose of this application is to show the potential of AR technology for supervision of industrial robot to increase work efficiency of human technicians on the factory floor. Yes, this application can be divided in 4 main functions. The first and most important is the AR-assisted robot monitoring, using panels overlays on the real world to monitor robot status. Then the second function is the AR-assisted robot control, in which the robot can be controlled using AR hand gestures. Thirdly, the 3D robot holograms for a collaborative experience. And finally, the robot remote control over a 5G network. There are
Karam,
different. Yes.
are you still on the first slide?
Yes. Yes. Okay. Yeah. So now I'm the right side. I will explain briefly the use cases that can be explored by combining augmented reality and with robots. One of them is the robot monitoring for factory floor support. It provides the AR visualization of production-related information to the AR user on the factory floor on real time. Other use cases like remote support and training can also be explored here. And finally, the roles and key dimensions of 5G on the fly retrieval of robot monitor information by the AR user. That's the first one.
Sorry, Karam, but we still only see your first slide.
Okay.
Maybe you can try to unshare and share again.
Can you see now this with a photo on the bottom?
I still see the title slide with the.
Very strange. Let me try to stop and sharing again. Just a minute. Can you see now?
Yes, now it seems to work.
Okay. So yes, so I was explaining the purpose and the 4 functions that we developed for this application, right? And now I was explaining the use cases that can be explored, like for example, this robot monitoring for factory floor support. Okay, and finally, the roles and key dimensions of 5G. So, for example, on the fly retrieval of robot monitoring information by the AR user, and edge-based storage of AR digital data to serve multiple AR headset units. Okay, so let me explain a bit in details the implemented solution. Hopefully you can see the slide with the title Solution Overview. Okay?
Yes.
Oh, perfect. Okay, so we developed an application to interface with ABB robot using Magic Leap 1 augmented reality headset. We integrated two sites, one placed in Brazil, where the AR user is located, and another one in Sweden, where the ABB robot is located. And the first challenge that we had was the connection on network layer, as we had to integrate the AR application to the ABB Robot Web Services. That is the framework, the ABB framework that enables external applications to access robot information and control. And then the second big challenge that we had was the integration on application layer, in which we had to integrate our Unit 3D design platform with ABB Robot Studio. That's the ABB simulated environment platform. And finally, our target in this project is to have a final demo setup as shown in the right side. That means all the sites are located in Sweden, connected via a 5G network, edge computing as a centralized repository of robot status information, and AR user able to monitor more than one robot. So our AR application is already being prepared for all this setup. And the last information that I want to show you, hopefully you can see the new slide. So we developed 3 AR panels for this application. The first one at the left side is the command panel that consists of AR-assisted commands to enable control of the arms movements of the robot. Then in the middle, we have the monitoring panel that consists of real robot data displayed in form of AR overlays. In the top, the robot information like ID, model, time information is available. And then behind, we have 4 robot status information. Operation time, to monitor how long the robot is in operation. System energy, to monitor the system energy consumption. CPU load, to monitor the robot performance. And finally, the robot health, to support robot maintenance time scheduling. And finally, we have a robot hologram panel at the right side that consists of a visualization of precise 3D hologram of the real robot. And we also have robot specifications and video instructions that could be used, for example, for training purposes. We can teach how to install the ABB robot without really having the real robot in front of you. Yeah, so that's what we developed. Now let's go to the video of the demo. Hopefully you can see it. So let's play now. So that's it. Any questions?
Thank you so much, Karam. Yeah, if you have questions, please again post them in the chat, and Karam and the team can either answer them directly in the chat, or we can take them at the Q&A at the end of this session. It is now time for a short 5-minute break. So please go and grab some coffee or just stretch your legs, and we'll be back in 5 minutes. Then describing the Kista trial site and the radio deployment there. See you in a bit.
Yes, thank you, Krister. Let me see if I can find the right one.
Looks good.
So, very good. So my name is Pietro Bruin. I work at Ericsson, and in this project, I work primarily with the Kista trial site and what is going on there. So before going into details, I wanted to give you some background general background on 5G. So 5G there you go. There are some animations. So there's a time scale, as you can see, for about 10 years, and that vertical line indicates where we are today. And 5G standardization started in 2015 officially. Already from start, the focus was clearly on industries, industry applications, machine type communication, etc. Besides, of course, the enhanced mobile broadband. And the first real 5G standard, so the first 5G release, that was release 15, and we're currently working with release 17 and starting up release 18 in the future. Already in 2014 or so, various 5G for industries initiatives were started up in different countries, and the aim with these were to engage with relevant industries to understand their needs and their requirements and what use cases they foresee, and of course also to promote cellular technology as a solution for wireless automation and Industry 4.0. The first commercial deployments of 5G, they were made first half of 2019, and public commercial mobile broadband services were offered first in North America, in Europe, and in Australia. I will come back to some technical details on the non-standalone or NSA later on in the next slide. The first so-called 5G standalone or 5G SA deployments and services were commercially available last year. And although we have now commercial 5G deployments in some almost 100 markets, 3GPP standardization continues as for all previous generations. The standardization is ongoing and developing. 5G Smart project was kicked off in 2019, almost 2 years ago, and as part of that, we have deployed networks in Kista and at Ericsson early 2020, and later the same year at ABB in Västerås. If we look finally at what has happened with the devices, we can see that in early 2019, really early 2019, we just had a handful of different models. Mid 2019, they were about 20, and today we're closing to 1,000. So there are now smartphones, pocket routers, industry routers, tablets, laptops, etc., supporting 5G. And the chipsets, some of them are already available in the 3rd generation. As a small note, the lowest price for any 5G smartphone that has dropped from around $1,000 US early 2019. In 2 years, it has gone down to around $100 US. So the cheapest 5G smartphone you can buy today is around 100 US. Still early days for 5G for industries, though. So with the risk of becoming a bit too technical, I need to say a few words about the different options in 5G. So early on in standardization, there was a strong push to accelerate 5G standardization and get something out on the market early. The solution was the so-called 5G NSA or 5G non-standalone, or option 3, as it also referred to. This option implements only the data plane over 5G, and the control plane, all the signaling for mobility, etc., is done over the 4G axis. So this was a quick way to introduce 5G communication early on. And as you can see in the orange box, there is communication over the so-called X2 interface between the 4G and 5G base stations, and the data traffic from the 5G non-standalone modem from and to is going primarily over the 5G, but also over the 4G access. So the practical differences are that 5G non-standalone requires spectrum both for the 4G and for the 5G. And then there is, of course, also need for both hardware and software support for both technologies. The good thing is that given that the initial hardware supports it, the upgrade from 5G non-standalone to 5G SA can be done with software. Now, to the deployments we have made in the project. If you remember the introduction slide, 5G non-standalone was the only technology available commercially late 2019, early 2020. So to get an early start, the decision was taken to go for 5G non-standalone in Kista. We should also remember that the first devices, they only supported 5G non-standalone as well. So it was a rather straightforward choice. So the Kista network is based on high band or millimeter wave spectrum. We're operating the 5G on 28 gigahertz. In these bands, there is more bandwidth available, but the coverage is a bit more challenging due to the higher frequency. So we thought it would be interesting to see how this high band would perform in a factory environment. The Kista network is a complete and fully localized private network. So every piece in the network, the basebands, the 5G EPC, the core network, the edge cloud, etc., everything is on the same premises as the factory test site or factory test area. And this is important to provide the best possible latency and security and survivability. And then things happened early 2020, as we all are aware. So to enable development and implementation of the different use cases at ABB in Västerås, there was a decision to deploy a similar 5G network also in Västerås. So in this case, we use mid-band spectrum. That is the 3.6 gigahertz band. We use the same 4G band, the 1800 megahertz. to anchor the control plane, same as in Kista. And also the Västerås network is fully localized. And as you have seen in the previous presentations and the video footage, we managed to do this development and 5G integration in Västerås. Going forward, you have seen these pictures before, going from Industry 3.0 to 4.0. To do this, there are a number of different things that need to happen. From a communications perspective, and in particular from a 5G radio perspective, one of the most important factors would be that we can send data within a bounded latency period for time-critical services. So the wireless access naturally has some latency variations. The wireless media is a shared resource, so there might be some slight queuing. There may also be retransmissions due to the varying radio environment, so some variation in the delay can be expected. For industry applications, this is sometimes, maybe even often, not acceptable. Late packets may be considered as lost packets. So the idea is to create as low latency as possible, and at the same making sure that the low latency is consistent. And the consistency we express as high reliability. And to get all the way, we have to create solutions for both low latency and for high reliability. And that is illustrated in the right part of the figure, that's removing the long tail in the latency distribution. So we have a bounded latency with a certain reliability. So to improve, that is to decrease the latency, there are a few tools, and we have listed a few here. So the first one is to use a wider subcarrier spacing to shorten the transmit time interval. So for instance, we use 120 kilohertz subcarrier spacing in the high band network in Kista. And then you can see you have 0.125 millisecond slot duration, and 30 kilohertz in the mid-band network in Västerås. And this actually means that we have slightly better latency performance in Kista because of the shorter transmit time interval. The second example is to bypass the normal scheduling request procedure. So if you have scheduled grants instead of sending the scheduling requests, you will save some time here as well. And there are different functionalities, similar functionalities with different names, so both for uplink and downlink to have scheduled grants. Third example is to use so-called mini slots. These are sent within the regular NR slot. You can see from the small green area, you could perhaps appreciate that this solution is not primarily for large packet transmissions, but because they're sent within the normal NR slots, you will gain some time here and improve your latency. The final and fourth example is preemption, and this means that you bypass the queue with your time critical transmissions. So you cut the queue and for the mobile broadband transmission, and these will be then repaired later on. Yes. Looking at the high reliability features, we have a few. They all come at some sort of cost. So the first example shows the possibility to use a more robust channel coding. This means that transmissions are less likely to be interfered. They are more robust, but the price you pay is that there is less room for payload or useful data when there is more coding used. So the other two examples are similar in the sense that they both impact the infrastructure and deployment. Multi-antenna techniques improves the probability that there is good reception and transmission. And there is also a possibility to combine different parts. The multi-connectivity solution adds also transmission points, including both radios and antennas, to secure that transmissions are properly received. These features are and solutions, they're standardized in 3GPP and later developed in infrastructure and in chipsets and devices as needs arise. However, before these things that will happen in the near future will be available, we can inform you about something that is happening right now. And that is, this is a press release from Ericsson a couple of weeks back. And as you can see, we have packaged something that we call Ericsson Private 5G, and that is now available to serve different verticals. And if you read carefully under the picture, you can even see that manufacturing is one of the verticals addressed. Bounded latency is not yet part of the package, but over time it will become available. So that is all for me. Any questions?
I think looking at the time, it would be great if again you post the questions on the chat and we can then pick them in the final Q&A. Thank you very much, Peter. Fantastic.
Thank you.
And then it is time for the final part of this webinar, which is the panel on future robotics and cellular communications. So I would like to invite our panel members to join me, and please turn on your camera if you can. I see Sebastian, I see Leefke. Let's see if I can also get Andreas on video. Not yet. Let me quickly check if he can. Andreas is having some technical issues, so he's working on it. But let's then get started, and then he can join us later. So let me introduce the members of the panel. So Andreas Bihlmaier hopefully will join us very shortly. There he is. Hello, Andreas. He is the chief software architect for ABB Robotics. And we also have Sebastian Elmgren, who is portfolio manager for smart manufacturing at Ericsson. And we have Leefke Grosjean, who is the project manager for the 5G Smart project. So the idea is that I will try to moderate some questions now in the beginning, and then towards the end of this panel, we will also try to pick up questions from the audience via the chat. And let me then start with, and I know Peter showed that picture, this Industry 4.0 picture, and one vision in that is that we will have more robots on the factory floor, so both mobile robots and stationary robots, and then you often hear about these fleets of robots. So maybe a question to you, Andreas. So how different is that compared to what we see today in the factories, and what are the steps that we need to take in order to sort of move towards that vision?
So I hope you can hear me now.
Yes.
Very good. Yeah, I think one of the biggest differences that is coming our way is mobile robots and mobile manipulation. And of course, once you go from untethering your device, you also need a way to keep it connected. So on the very basic level, 5G will help us to get to reliability in wireless connections that is much closer, hopefully, to a wired connection compared to your usual Wi-Fi setups. In terms of what we just hear, determinism, bandwidth, redundancy, and also flexibility when it comes to moving about the larger facility. That is definitely the very basic one. Where it then really gets interesting is looking at once you go to a mobile setup or mobile manipulation, that your capabilities are also different, that you need to interact with a less structured environment, that you want to add more data-driven capabilities, less fixed programs, have more models of your environment, need to do more object recognition or path planning, SLAM, as we have also seen earlier today. You might need to teach the robot more often than just program it once and run it for a year or two. And I think here also having a flexible connectivity solution can help you to kind of add those skills or add those capabilities on demand to your robot. Because today, either it is contained on the robot controller or it's not available, or it will be available in the next release. But if we think about over-the-air updates or also being able to put, let's say, new capabilities into the loop by connecting them over a reliable Wi-Fi or 5G connection, that is definitely a demand that is coming up for such newer types of robotics in general. I think it's a very important contributing factor that you can outsource parts of the intelligence to the infrastructure or even the internet, and you want to be flexible instead of having to do a point-to-point connection between all of them.
Right. So maybe a kind of a similar question then to you, Sebastian, because obviously cellular communication, we use it to connect people and provide services at airports and malls and sports arenas. So I mean, that we do. How different is that compared to connecting hundreds of industrial devices or robots in your mind?
I think one difference which now 5G is introducing is that this is made for machine-to-machine communication, and that means that it can adapt to many different use cases. So we can cover everything from a simple sensor to video applications and robotics, more real time, all with the same infrastructure. So if you look at just covering people, they are quite similar. They need the same kind of service, but looking at a factory, each application will require their own performances and services. So 5G can adapt to that. So where you previously would need to have a Zigbee network, a Bluetooth network, a cable network, a Wi-Fi network, and so on, now that all can be simplified, and we can have one infrastructure for all of these applications. So I think that's a strong thing for the manufacturing companies.
Right. And I was also curious, Andreas, when you mentioned this need for flexibilities, how do we realize that without adding complexity or even increasing downtime for reconfiguration, etc.?
I think in general, the trend in IT, computer science, and robotics has been over the years, the complexity is always increasing, never decreasing. If you look at, you have a very simple robot with a very simple controller. Even if we go 30 or 40 years back, it was dedicated hardware just to do one specific task. Of course, that is somewhat simpler than having freely programmable hardware, general purpose solutions. But what we usually do then is, if the complexity increases, we go to the next level of abstraction, so that we look also more into having a middleware for robotics that abstracts away from the deployments to one particular controller, and perhaps also abstracts away from how do I connect robot A with robot B, how do I make sure that in a fleet of robots, they coordinate among each other. So there will be definitely added complexity in the system level, but also through this new possibilities that you get from it by having basically every device connected to the internet, or at least to your on-premise edge devices and your on-premise installation. If you take connectivity as something that is given and that is stable and more or less reliable, of course, then you can build on that, and you can solve problems in a different way. Today, if your robot shuts down, has an error, someone has to walk there, pick up the teach pen and see what the error is. If I always start from a point where everything is already connected and I can manage it from a central point, then we can also address problems that come up with the added complexity at the same time. So I think in the end, we wouldn't do it if we wouldn't have more benefits than drawbacks from the solution. And I definitely see it as many new possibilities coming up if by default things are connected once they are powered on.
Right. So is this sort of this flexibility that is the one of the goals, I guess, in smart manufacturing? Is that also impacting sort of your networks, Sebastian? That you also need to take that into account?
Yeah, definitely. I mean, and I think that's again something where 5G or licensed technology plays a crucial role, because we can have reliability by design. So we know when we deploy a network, we can see what kind of performance we would have where in the network, and it doesn't vary as much as you would see in an unlicensed spectrum where you have unknown radio transmitters and so on. We know what performance that would be. And it's also easier to create coverage in a factory, which then open up for this flexibility, because you don't really know, where will you have your robots in the coming half a year or whatever. You need to move things around, and then we can have a network that is designed to cope with that, and everywhere in the factory where you could put a robot, you would have good coverage, and you don't need to then reconfigure your network while doing that. We can have a foundation that approves of this flexibility.
Right. And now I think I want to also get you, Leefke, into the conversation. So I mean, Industry 4.0, smart manufacturing. We've seen the use cases that we're working on in the 5G Smart project, and obviously there are research challenges still that we need to address. So how would you say that 5G Smart is addressing or sort of pushing the research in this area?
I think 5G Smart as a EU project, it might look now from this webinar as if we are doing a bilateral collaboration here between Ericsson and ABB, but 5G Smart as a whole, that puts everything into a wider context. We are a whole consortium of partners working together. So we're really building and taking input from the whole ecosystem, I would say. So we have ICT partners, OT partners, academia, operators in the entire project. And this really gives us the possibility to work together and see things in a wider perspective. And I think even the fact that we're financed by the EU gives us actually this possibility to really focus on research within the 3 years that the project is running, and really get the commitment from all of the partners to this as well. And I think that really plays a crucial factor of having the possibilities to bring together people that are from different areas into this and work on this ecosystem together.
Right. One more. Let's go ahead.
Sorry, just a short comment. I think the term ecosystem that you mentioned is very important, because it's not just robots doing their thing, machines doing their thing, and the manufacturing execution system expecting something else to happen, and the humans and workers doing a third thing. So having by default kind of a mesh or interconnection of different devices, them being able to speak a common language on different levels of the protocol stack, I think that's an important part to it, because today we very often still build point-to-point solutions. You connect this robot with this machine, and then they can talk to each other, but that doesn't help you at all to connect now to the next robot or the next machine or the ERP system. I think this intra-connected web of devices, because you build them in a way with the expectation that yes, they are connected, that this is not, it's like, is that powered by electricity? Nobody asks that anymore today. And I think in some not too distant future, no one will ask you anymore, is that device connected?
Right. And on that sort of note, do you also think or see that, I mean, wireless communication is obviously fundamentally different from a wire or wired connection. Do you also see the need for sort of robotics applications to adopt to this? Or are we simply pushing requirements on the communication?
So from my side, we shouldn't do everything over the wireless network. If it doesn't help or bring any value to disconnect the low-level servo control loop from its motor, because you need the cable anyway, because you cannot transmit that much power without the cable to the manipulator. So then why not keep that connected through a wire and focus more on higher level skills that might also require quite strict guarantees when it comes to latency, jitter, bandwidth, and so on. But I perhaps wouldn't put things unnecessarily on a wireless connection where I need to run a cable anyway. But of course, the good thing is about the wireless connectivity, well, you don't need to plug in a cable, and that cable doesn't need to plug in somewhere on the other side. So if I just turn it on because I need to, supply it with energy anyway, but the rest is then just works. I see a new device is available in my factory, and then I can identify what it is and what it should do and so on. That solves already many problems. But I wouldn't shift everything onto the new medium and force it for means where I might not even need it. Especially when it comes to the tight inner control loops. I think they are not our problem usually. Them you can run locally because you don't need any external information. But for the higher level capabilities, you do need information about the environment, about the purpose of what is supposed to happen. And for that, I think it will be very valuable, not for controlling your individual motor.
So I have a long list of questions, but I also see that we're starting to run out of time. So I would like maybe Peter or Ognjen, if you could moderate some questions from the chat, if there are any. I haven't had the possibility to follow the chat.
Not to the panel as I can see. There is one question. Are you planning to do some evaluations on network slicing for industrial environments, multiple competitive applications? I think we can respond to that one. There are no plans to do that. The reason being, we have all these use cases now implemented, and we expect to be capable to run them in parallel without any major issues. The traffic load will still be very low load. But yes, for sure, there is a possibility to use quality of service framework or slicing to create differentiation or priority. So we may do that if we see the need for it.
Right. Okay, but then I can take the opportunity then to ask a final question then to Andreas and Sebastian. And that's and I guess we can start with you, Andreas. That's regarding human robot interaction. And we saw some demonstration video earlier. Obviously, for the foreseeable future, I mean, it won't be only robots in a factory. The human worker will still play an important role. How do you see that human-robot interaction evolving?
So I really like the demo on having a more, let's say, situated UI, or a more, spatially located way of interacting, because it feels always a bit strange. I have a robot here that is supposed to perform some task in the environment, but then I'm staring at the screen all of the time, and so kind of there's a big disconnect today between that I want to program a device to interact with the physical world, but then I'm kind of constrained to my screen. So if there's a natural match between doing things on your screen when you build an application for information data processing that doesn't have to do anything with the physical world. But since it is about interaction in 3 or more dimensions, having this more natural user interface, and thereby a better user experience, and having more possibilities when you can visualize, what's going on, what will the motion be, where is the robot seeing or planning to grasp a part, when I can actually look into the application cell through an AR device or similar, or mixed reality, will definitely improve building robot cells, commissioning them and adapting them, or also doing maintenance and support tasks. I think freeing robot programming from a screen is definitely very, very interesting. But of course, that means you need to be closely synchronized with the robot controller, with perhaps other peripherals or cell equipment. And again, the question is how to do that. Do you really want to walk around with a headset with a cable plugged into each and every device? So obviously no, so we need a better solution, and 5G is definitely the best one today.
Yeah, I guess, Sebastian, that you also see 5G as an enabling technology for this application.
Definitely, and I think also it's a democratization of the technology, because with this wireless technology we can take the system support previously only available in back office in the hands of the people on the shop floor. So the people in the front line would get the system support and the means to take decisions, which they don't have it right now. So I think that really will be a change, and also how organization works, who takes decision about what, when you can have those kind of tools in the hands of the operators.
Right. Okay, and unfortunately we are out of time. First of all, a big thank you to the panel members. Thank you for sharing your insights and ideas on this interesting topic. Thank you to everyone that prepared and presented today, and thank you also for the audience who joined this webinar and posted questions on the chat. I hope to see you all again in a future 5G Smart event. Stay safe, and bye-bye for now.
Thanks for the interesting webinar. Have a nice day.
Thank you. Bye-bye.